Welcome to another fabulous day in Calculus 3. We're going to be doing Lagrange Multipliers method, and it is exciting because it's a cool way to extremize or optimize a function, especially if it's a function of 3 variables, which we're going to find out. Okay, so this lecture is inspired by my old mentor who passed away in 2013, Dr. Arnold Vallone. In fact, I based this lecture on when he came to my Calculus 3 class and guest lectured. So this has a very different flavor, and I hope you enjoy it. So let's do the method here. So quick review of what you already know how to do when it comes to optimizing a function, meaning finding a max or a min. So let's say somebody gives you a function of 2 variables that looks like that, z equals f of xy, and you find where both the partials, df dx and df dy are 0, and you go get those critical points by solving the system. And then you do the d-test, also known as the second partials test, to see what kind of extrema it is, or maybe it's a saddle point. Now, with the Lagrange multipliers, which is this new method we're about to look at, you already know there's going to be a max or a min, or maybe even both. So you don't do the d-test ever when you use this new method, which is kind of cool. So that means you don't have to find any second partials when you're doing this method. Okay, so let's start a problem and then act like we're going to solve it in the way that we already learned how to do. And then in the middle, we're going to stop ourselves and go, meh, I don't feel like it. Looks like too much work. And then we'll try a new task, okay? So here's the problem. It's a word problem, of course, Let's say you're given 1,000 square feet of material and you want to make a rectangular box. Find the dimensions of this box that would make your volume a maximum. Okay, so you've got this box here. Great. And you've got a width, a length, and a height, x, y, and a z. And you know that your volume is equal to x times y times z, the width, the length times the height. But you do have a constraint here. And the constraint is 1,000 square feet of material. You can't just make any old box you want. You have to work within the confines of your constraint. Now, you do get to assume that your x, y, and z are positive because, you don't want to try to be making a box with negative dimensions. So we are going to restrict our domain here for this volume function. So, let's say you want a really large base of your box, or maybe you'd like to make it really tall and save the material for the sides, or is it a middle ground between putting all your 1,000 square feet of material on the base and the sides? So there's got to be some sort of maximum there. So this constraint here is surface area because it's square feet. So we know surface area for a rectangular box is 2xy, that'd be the bottom and the top. And then there's 2 of the ends, xz, and then there's 2 of the sides, 2yz. And we want this surface area to equal 1,000 square feet. So this isn't the equation that we're going to do calculus on. This is an equation for the constraint. Okay, so now what? We want to maximize V, which is equal to x, y, z, subject to the constraint. Well, we so far can only get the max or min of a function of 2 variables. So what we're going to need to do is reduce V to a function of 2 variables only, because right now it's a function of 3 variables, and we can't do that. So how do we reduce V to a function of 2 variables instead of 3? So what we do is we use the constraint and solve it for one of the variables. Let's solve the constraint for, say, Z. Okay, so here's your constraint. How would you solve that thing for z? Well, first what I'm going to do is I'm going to divide both sides by 2 just so I can reduce the equation itself. So I'm going to have xy plus xz plus yz equals 500. The same thing as that what we had before. To solve for z, I'm going to first subtract the xy from both sides. And then I'm going to notice that the two terms that are left, you can factor out a common factor, which is z. So when I factor out the z, the other factor is x minus y. And then finally, to solve this for z, I'll divide both sides by x minus y, right?
Is it x
plus y, sorry. I'm really tired today, thank you. So now I'm looking at this and I'm like, okay, I solved it for z, now what? Well, you're going to use this to reduce your volume to 2 variables. So you're going to go volume is x times y times z, but in place of the z, you're going to substitute 500 minus xy all over x plus y. So now your volume function is a function of x and y only, but it looks kind of horrible like that. So if you were going to go find the max or the min of this volume function, you would have to find Vx and you would have to find Vy. And both of these would involve the quotient rule, and it'd be a little bit painful and yucky. Okay, so I'm going to stop right there and go, I don't feel like doing this. This looks really not fun. So I'm going to put unhappy face. Okay, so note this problem is starting to look pretty involved. So we could finish the problem using all our previous knowledge, but let's stop and ask ourselves a question. It's a very good question too. Why is it always that the z has to be dependent on the other 2 variables? What if we reduce the volume function to say, instead of x and y only, y and z only, or x and z only? You know, it always seems we're always like killing off the z. That doesn't seem very fair. So I'm going to put not fair. That's what Dr. Vallone used to always say. That's not fair. And in fact, I can show you an advanced mathematics example where when you solve for a different variable in terms of the others, you get a different answer. Yeah, so it can be dangerous. All right. So if you want to see that, let me know and I'll show you during an office hour. So it could be the wrong way to go. What we're doing right now, and we're stopping. Now, Lagrange never takes you in the wrong place. That's what's so good about it. So what does Lagrange do? Lagrange is the guy who came up with this Lagrange method. He tells us, hey, instead of trying to reduce this volume to a function of 2 variables, no. Keep the volume as a function of 3 variables, because it's fine. And you're going to introduce a brand new variable into the whole conversation. What? We already have 3 variables and we're going to introduce a 4th variable? Yeah. Another one. And this variable is known as lambda, and that's a Greek letter. So you may want to try to draw it appropriately. That's lambda right there. That's lambda, Greek letter. And this is known as the Lagrange multiplier. This lambda. Okay, so now what? Well, what you're going to be doing is you're going to extremize.
Is that a half-life symbol?
The half-life.
Well, it's a video game reference.
No,
but
they use that symbol for half-life though.
Oh,
okay.
actually, yeah, yes.
I'll believe you, and let's move on. Math is the queen of all the other sciences, so I imagine there's a lot of stuff that, I mean, with Greek letters you can do. You know, like in electrical engineering, omega is used for frequency. Okay, so there you go. So we're going to introduce this new variable, and what the Lagrange method is going to have us do, it's going to have us extremize a function of x, y, z, and lambda, all 4 variables, subject to this constraint, big G of x, y, z equals 0. So this function that we're going to extremize, so we're going to create a brand new function, Lagrange. I'm going to call it the Lagrange function. It's going to be a function of 4 variables, and it's going to be f, x, y, z, and this is the function that you're trying to optimize. In our case, it's going to be the volume. Minus lambda times big G, x, y, z. So this is a brand new function we're creating called big L. This is very different from the way the textbook does it, and I want you to do it my way to get maximum credit. If you do it the way the book says, I'll give you credit, but not full credit, because I want to catch who's watching my videos and doing it this way versus people who are not. And you guys are all here, so kudos to you. Here you go. In our box problem, the big F is the volume function. And the constraint, which is big G, is the surface area function. That's the xy plus the yz plus the xz, and we subtract 500 from both sides because we want the constraint to be equal to 0. So with this Lagrange multiplier method, you don't have to solve for the z variable in terms of the other variables at all. So that's kind of cool. What we're going to do now is we're going to find all of the partials for our Lagrange function. And since our Lagrange function, this big function L, is a function of 4 variables, we have to find 4 partial derivatives. You got it. That's going to be the little bit tricky part. Because you're going to set all 4 partials equal to 0 and solve a system of 4 equations and 4 unknowns. But it turns out we usually don't need to solve for lambda, so it's really 3 unknowns. Okay, so we're going to solve a system of equations like this. You're going to get Lx, which you could also write as dl dx, which, since our big L function is big F minus lambda g, it's going to be the same as finding the partial of f with respect to x minus lambda times finding the partial of g with respect to x. And then Ly, which you can denote dl dy, will be fy minus lambda gy. Lz will be dl dz, which is fz minus lambda gz. And L lambda, when you hold all the other variables constant, the x's, y's, and z's are all held constant. The derivative of f, x, y, z with respect to lambda is 0. And then the derivative of minus lambda g, x, y, z is just going to be negative g, x, y, z. And then you're going to set all these partials equal to 0 at the same time, all of them. Now, here's the good news. I mean, the bad news is you've got to solve this big old system, which is typically nonlinear. The last equation is actually the same as the constraint equation. If you multiply both sides by -1, it's going to give you the same as your constraint, which is kind of good. Doesn't mean you're going to ignore that equation, because that's going to basically be the one that you run to at the very end when you're trying to solve for all the variables. Okay, so you need to solve this system. We're going to do a lot of examples, so don't worry. In fact, I'm going to spend like today and the next time on this stuff so we can get through lots and lots of examples. I want you to really have this down cold. Okay, now Dr. Arnold Malone, of blessed memory, used to say that lambda is an angel variable. I love this. And the angel comes down from heaven to help us out, and we rarely ever even have to figure out what the value of the lambda even is. This comes to help us out. You don't have to solve for it or figure out what value it is. Now, there are some people who actually like to solve for the lambda, which is typically not us. Yeah, economists and physicists, when they use the method of Lagrange, which they do, they a lot of times care about finding that actual value of lambda. Who knows why? They just do. Okay. Now, when you use Lagrange, it's not really fun or interesting if you have functions whose gradients end up being the zero vector, because then you can't really do anything. So we're going to restrict ourselves to regular functions, that is, functions whose gradients are not the zero vector. So in other words, we want the gradient of f, which we could also call grad f, not equal to 0. And we want del g not equal to 0, which is also known as the gradient of g, grad g. That's how physicists refer to it. They call it grad. Now, your textbook doesn't really use this idea of this Lagrange function. Your textbook's going to tell you something else. But before I show you what the textbook says, I want you to look at these equations here. If I rewrote everything, where I wrote fx is equal to lambda gx, because I added lambda gx to both sides, and then add lambda gy to both sides to get fy equals lambda gy. And similarly for the fz, what are you looking at here? What you're looking at is all of the components of the gradient of big F all look like they're multiples of the components of big G. So another way I could write this is that del big F, the gradient of F, is going to be equal to the lambda times, I'm running out of room here, lambda times the gradient of G. And then you distribute the lambda, or let me pull up I need to show this because this is kind of important, new piece of paper. See, so that we're basically saying this. But this over here on this side is a big old vector. And that's equal to lambda times another big old vector, because we know gradients are vectors. And when I distribute this scalar over here, the lambda, the helper variable, our angel from heaven, also known as the Lagrange multiplier, then you equate the vectors. So the vector on the left had better be equal to the vector on the right-hand side. So that means that fx is equal to lambda gx, and so on and so forth. So the way that your textbook is going to give this Lagrange method is they're going to basically give it to you like that. There you go. And they sometimes use little f and little g, so I'm not going to do it that way. But my way and the book's way are really the same. It's just that I'm talking about extremizing a big function L, who consists of f and g, and our Lagrange multiplier. That's all. So I'm not teaching you some completely different approach that has nothing to do. It's really the same. Now, am I the only one who teaches it this way? No, there are other textbooks that do teach it this way that I'm showing you, where you have this big mother of a function, big L, the Lagrange function, and you extremize that. That's how I roll. Okay? Now let's go finish our problem. And as Arnold would say, time for hand-to-hand combat. He was a really big World War II buff. I miss him. So who are we trying to maximize? We're trying to maximize the volume, which we're going to call big F. And that's length times width times height. So x times y times z. And then the constraint, the big G of x, y, z, was that surface area constraint. So x, y, well, I divided it by 2 is the way I'm going to use it. Minus 500 equals 0. And so the Lagrangian function, and this is what I want you to do on your handwritten work to get full credit, we call it big L. And big L is a function of 4 variables, x, y, z, and this mu variable, lambda. And that's always, and that's always going to be equal to f, x, y, z minus the lambda, the Lagrange multiplier, times your big G. So what does the Lagrange multiplier, or Lagrangian, look like for us? It looks like x, y, z, because that's the function we're trying to optimize, minus lambda times parentheses x, y plus xz plus yz minus 500. This is the function we're trying to extremize, if you will. And we're going to find its critical points, stuff like that. So let's get the 4 partials for this big Lagrangian function. 4 partials, 1 for each of its 4 variables. Here we go. So take the partial derivative with respect to x. Well, the partial derivative of xyz with respect to x is yz. And remember, when you're taking the partial with respect to x, you're holding y and z and lambda constant and taking the derivative with respect to x. So minus lambda, that's a constant, times what's inside parentheses, derivative with respect to x. And I get just y plus z, parentheses. And we're going to set this first partial equal to 0. We're going to set all the partials equal to 0. Now let's go get the partial with respect to y. Hold x, z, and lambda constant. I get xz minus lambda, parentheses, x plus z when I differentiate with respect to y. Set that equal to 0. Then differentiate all over again with respect to z. Hold x, y, and lambda constant. So I'm going to get xy minus lambda, parentheses, x plus y, set it equal to 0. And then L lambda, since you're holding x, y, and z constant when you're differentiating with respect to lambda, the first term, the derivative of x, y, z with respect to lambda is 0. Cool. And then you have a minus, and the derivative of that last big old term with respect to lambda. Well, it's just going to be everything that you see inside the parentheses. And then you're going to set that equal to 0. And I claim if you multiply both sides by -1, this is really the same as the constraint. Okay, now the interesting part, to do the algebra. Okay, sometimes this is the part where students can't do. They do fine with advanced calculus, you know, make them do something really hard, like find a horrible directional derivative. And then I ask them to do some algebra and solve a system, and then they fall apart. Uh-oh. Okay, now folks, this system here is definitely nonlinear. Okay, oh my goodness. It's not a linear system at all, not even close. Okay, so you have to be really careful when you try to solve it. In general, for most of these problems you're going to do in the homework, the way I approach it is I solve for lambda 3 times and then set the lambdas equal to each other and try to get the variables in terms of one of the variables. And if that sounds like, what the heck did I just say? Don't worry. As I go, it'll hopefully become more clear. So take a look at this first equation. If you solve it for lambda, you know, by adding lambda y plus c to both sides and then dividing both sides by y plus c, you'll get lambda is yz divided by y plus c. I'm going to call this equation 1. So you're going to solve for lambda again when you're looking at the second equation here. Oh my. So I'll call that equation number 2. I solve for lambda for a second time, and then I'll get xz divided by x plus z. Oh my. And then I look at this third guy and I solve for lambda again. Oh man. Okay. Then what? Now, these lambdas have to be equivalent. You can't have one lambda be equal to 7 and the other one equal to -1. They have to be equivalent. So what I'm going to do is I'm going to set lambda number 1 equal to lambda number 2, if you will, and see what happens. Okay, I'm going to try to get all of my variables in terms of x's. If you have a favorite variable between the x, y, and z, then you try to get everybody in terms of that favorite variable. I usually make my favorite variable x, so everybody has to be written in terms of x. That's how I roll. Okay, so pick one. Pick a lane. Don't pick a multiple lanes. Well, I'll get him in terms of X, and then I'll get that guy in terms of Y, and then this other guy in terms of Y. No, 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 no. No, you do that, and you're going to get confused, and you're going to get really frustrated, and then you're gonna hate on all these Lagrange, and you think it's, oh, I can't even solve the system. No solutions. No, there's a solution. Okay. So I want lambda to be equal to lambda. So the first lambda looks like yz over y plus z, and that needs to look like the other version of lambda, which is xz divided by x plus z. Now I'm going to multiply both sides by the denominators to clear fractions. That's how I roll. So I'm going to multiply, assuming that we're not multiplying by 0. We don't want any of these values to be 0. And we already agreed the domain is where width, length, and height are all positive. So we're safe. Now reduce to lowest terms. Okay, those cancel, those cancel. Over here, I have yz times x plus z. Over here, I have xz times y plus z. What a mess. Let's distribute to get rid of parentheses and then look at what we have. After distributing on the left, the first term is xyz, and then the second term is yz squared. On the right, I have xyz plus xz squared. I hope you can tell by looking at this equation that if I subtract xyz from both sides, it's gone. And now I have yz squared is equal to xz squared. Assuming z is non-zero, let's divide both sides by z squared, and I get y in terms of x. Save this for later. Good for me. I got one of the other variables in terms of x. In fact, really easy. Y is equal to x. Cool. Now what? Well, I'd like to get z in terms of x. Okay. So now let's set the first version of lambda equal to the third version of lambda and see what happens. Okay, because you need lambda to equal lambda. Okay, so yz over y plus z has to equal xy over x plus y. Great. Doing the same thing as I did before, multiplying both sides of both sides of the equation by the LCD, if you will, to clear fractions. And then reducing, x plus y's cancel on the right. On the left, the y plus z's cancel. Oops. And then distribute to get rid of parentheses. So now I have xyz plus y squared z is equal to xy squared plus xyz. I hope you can tell that again, I can subtract xyz from, is that supposed to be a plus, sorry, xyz from both sides. And then I have y squared z is equal to xy squared. Again, assume y is non-zero, divide both sides by y squared. And then I have z is equal to x. All right, cool. Now what? You have x and y, and excuse me, y and z are now in terms of x, which is really nice. Why is that awesome? Because what you're going to do now is you're going to use that third equation. I bet you thought we weren't going to use it. This one here, which is essentially the same as your constraint equation. So I'm going to plug my y equals x and my z equals x into my constraint. Now remember that your constraint looked like, you know, xy plus xz plus yz equals 500. And if everywhere you see a y, you substitute x, and everywhere you have a z, you substitute x also, you're going to get x squared plus x squared plus x squared equals 500. Cool. Yeah, we're getting closer. Why is that awesome? Well, because now we have an equation with a single variable in it. So if I add all the like terms together, I have 3x squared is equal to 500, or x squared is equal to 500 thirds. And now you know I take the square root of both sides. What do you always have to remember when you square root both sides of an equation? Somebody.
Plus or minus?
Yes. You got to have that plus or minus. Now, for this particular equation or word problem, we are going to ignore the negative. What for this problem? Don't always ignore it. This is sort of a problem where we talked about it wasn't okay to have a negative. So we will ignore the negative for this problem. Why? Not for every single Lagrange problem. Why is it okay for this one? I'll give you a hint. I'm going to draw you a picture.
If I remember correctly, wasn't it because we put constraints where X, Y, and Z were all greater than 0?
Very good. Yeah, we don't want to have a box with 0 or negative dimensions. That would be a very uninteresting box. No fun. So we're going to ignore the negative for this problem, okay? Because we only want positive dimensions here. So then what? Well, X is going to equal positive 500 thirds. And I can reduce this a little bit because 500 is the same as 100 times 5. And a square root of 100 is 10. It doesn't make it look that nice. But 10 times the square root of 5 thirds. And now remember that Y and Z are also equal to X. So they're also going to be 10 times the square root of 5 thirds. Okay, so the dimensions are 10 square root of 5 thirds times 10 square root of 5 thirds by 10 square root of 5 thirds. And so our max volume is going to be equal to the product of all this. And when I multiply these three numbers together, I get 5,000 square root of 5 over 3 square root of 3 after I do some simplifying, cubic, and I think our dimensions were in feet, so this is cubic feet. I don't have to do a d-test. I never have to find second partial derivatives when I'm using the method of Lagrange. I'm done.
Question.